Hello and welcome to our presentation. I hope you enjoy. My name is Mila Stosic and I will be explaining my team and I's overall problem and objective we plan on completing. The problem we have been challenged with is aiding in the production of a CubeSat for the Canadian Satellite Design Challenge. The Queen's Space Engineering team has requested my team and I to design a visible light communication system on the satellite. This VLC system would aid in identifying the satellite amongst its launch cluster and function as a backup communication method if the radio system should fail. The hardware component must be able to send light signals from orbit and be received on the ground, and the software element must be able to receive any command message from the satellite and convert it into a light-compatible medium that can be translated back to the original message. The overall objective is to design both a transmitter and receiver apparatus. The design will include a working encoding algorithm that takes input from the satellite and converts the data into transmittable message. On the ground, a similar decoding algorithm will be applied to convert the messages back into the readable data. Error correction will be integrated into the software component to ensure that the VLC system will be functional across a noisy channel. The original scope included making the design modular to be used either in the CubeSat or balloon applications. However, the team's final design will not be capable of functioning in daylight conditions, which is a requirement to the balloon system. So the design will focus on the CubeSat application.
The solution was evaluated in accordance with the objectives set at the beginning of the project. The first objective was the ability to send receivable visible light messages from an altitude of 400 kilometers with a maximum distance of 450 kilometers. The laser chosen for implementation has an irradiation angle of approximately 1 microradian. Through simple trig calculations, it was determined that our transmitter design would produce a readable message on the ground using a parabolic receiver dish. Another goal of the solution was being as mass and energy efficient as possible. In evaluating the various potential solutions, it was found that the laser transmitter model was the most mass and energy efficient. Finally, the solution was evaluated for its cost efficiency. Throughout the process of finding a solution, the laser option seemed to be the most cost efficient. However, the team received a quote from Unique Lasers for the specific laser used in our design, and the price is not very feasible for this application. Improving the design. As previously mentioned, the cost of the laser was unreasonably costly and not feasible. This is something that would have to be improved upon if it were to be implemented on the CubeSat. To improve our design solution, the team also could have incorporated radiation proofing into the code to reduce the harmful effects of radiation exposure in space on the transmitter, improving the efficacy of the system to transmit messages as needed. This would require more research and time to complete, which was limited in this project. Additionally, the testing of our prototype was qualitative and not quantitative. It would have been more beneficial to QSET for us to have quantitative data to prove that the concept of our design is successful.
The guiding question to our design process was how. How will we be able to send a visible light signal through over 400 kilometers of atmosphere to the ground in a decipherable manner? To do this effectively, the transmitted light, or absence of it, must create as large of a change in luminous flux at the surface of a photodiode on the ground as possible. For this will induce the greatest electric current into our receiving circuit. This means that the light coming from the transmitter must be as concentrated as possible, and the receiving module must be able to focus a large amount of light into the diode for the best results. And to send the most concentrated beam of photons, the team chose a laser over any LED configuration, as the lasers had a much lower diffraction angle, keeping the beam more concentrated throughout over the distance. Red light was also chosen as a color of light to be emitted, as red wavelengths are the least likely to be dispersed while traveling through the atmosphere, as you can see with sunsets and things like that. And in this setup that we have described, the greatest number of emitted photons at the transmitter would make it to the receiver module on the ground. And at this receiver module, the team opted to use a reflective parabolic dish over a focusing lens, with the thought being that more light could be reflected into the diode than would be refracted through a lens. Because we were only looking for red wavelengths, a red light filter can be placed in front of the photodiode to increase the relative strength of the signal from the background light. The final transmitter design also included an Arduino Nano to receive and encode the message from the satellite, as well as aerogel insulation to protect the circuitry from thermal changes and some radiation protection. On the ground, an Arduino Uno was selected to be part of the receiver circuit that measures the voltage difference across a pin with respect to the current induced by the photodiode. The images and circuit diagrams shown on the screen are of the team's prototype, with the design intention for the circuits to keep them as simple as possible, so there would be less opportunities for something to come loose during a launch scenario in the actual model.
The system to send the message is based on two identical libraries made of 32 characters and their unique 5-bit strings. One is used by the transmitter and the other is used by the receiver. The characters in the libraries can be whatever the satellite team deems necessary. In this example, our message, hello world, is converted into a string of bits using the library on the transmitter. Then the error correction system is set up with Hamming code. This adds a few extra bits to the message and allows it to detect and correct errors that occur over transmission. The signal is then sent by the laser, turning off and on for each value in the list of bits. The data that the receiver receives can be represented like this. Each point in time that is measured has an output value proportional to the strength of the light at that time. There are two elements affecting this output: the brightness of the transmitter, which changes the size of the steps, and the amount of noise, which changes the random offset of the output. The receiver could pick a value and call anything above that a 1, anything below that a 0, but this system would break at locations like this. Instead, the receiver looks at the amount the value changes between each step. The number of each size of change are plotted on a change distribution graph looking something like this. There are 3 bumps on the graph. One is in the center where all the changes of 0 and all the small changes caused by noise. And the ones on the outside are the positive and negative changes caused when the transmitter turns on or off. By finding the location of the outside bumps, the receiver can go back to the data and identify where the signal turns from a 0 to a 1 or vice versa. The system will fail when the noise is too large and the bumps overlap, or when the signal is too small and the bumps overlap. Both of these are different ways of saying that if the changes in the ambient light levels between each time step is as large as the changes caused by the transmitter, then the system will fail. Assuming that the system succeeded, the decoded list of bits is checked for errors using the error correction system that was put into place before transmitting. Finally, the list of bits is matched up with its respective characters from the receiver's library to get the original message.
Incorporating other factors into our project, socially there wasn't much to incorporate, but we did take into account the impact that the cost of our actual model would have on our stakeholders, the stakeholders being Queen's Space Engineering Team as well as Queen's University or the Design Challenge, who presumably would be funding the actual model if it were to be used by QSET. Environmentally, we took into account light pollution, carbon emissions, and also carbon intensity during building and operation. But due to the compact size of the VLC system, light pollution and carbon emissions would be negligible. And as for carbon intensity during building and operation, it would be roughly the same no matter which design solution that we chose. As for technology-wise, our software, one of the things that we took into account was the available storage that we had. For example, we weren't able to radiation-proof the software because there was not enough storage to include redundancy checks. As for the hardware, we wanted to look for materials that were attainable by QSET. And financially, we wanted to make sure that the cost of our prototype was within the given budget of $90, as well as making sure that the cost of the actual model was feasible, which unfortunately, as you can see by the cost breakdown of the actual model, was not possible since due to time constraints, we weren't able to find a laser that was reasonably priced and also met the requirements of our visible light communication system.
Delivery and disposal plan. If our project is selected, it will be delivered to the QSAT project build site in fully assembled form. This of course consists of the individual transmitter and receiver components. The code found in Appendix 5 of Phase 4 will be emailed separately. For the project disposal, the finished prototype will be disconnected and disassembled as cleanly as possible. Then the borrowed parts will be returned. With the remaining parts, our project group members will likely find use for them for the basic electronic components in future personal or educational projects. The more specific parts, however, for example the photodiode, will be recycled at an e-waste drop-off site. Waste Connections Canada has a Kingston site at the address shown on slide of 1266 McAdoo's Lane. All remaining parts will be dropped or will be recycled there as well.